Good afternoon to everybody, and welcome to about particle-based simulation. The agenda of the meeting, of the webinar, is shown here. So a very short introduction about Enginesoft, and then about Particleworks, the software based on the moving particle simulation method. That is the topic of this webinar. I will focus mainly on applications to show you a list of applications as wide as possible, and then I will show you how to use the software. First of all, I forgot to introduce myself. Massimo Galbiati speaking from Enginesoft. I'm responsible for CFD at Enginesoft in Europe, and I'm product manager for Particleworks software. Start with a very short introduction about Enginesoft for those who don't know about this multinational company who is mainly focused on simulation-based engineering. Enginesoft, as I said, is a simulation-based engineering company mainly focused on selling CAE software in Europe, doing consulting activities using the same software. We are acknowledged by the European community and by the Italian Ministry for Education and Research as a research lab. So we can participate in and also coordinate research projects. And we have also a long list of training, both on theory and methodology of simulation and on specific software training. So these are the main four pillars of Enginesoft activities. And we are active in different European countries, starting from Italy, Germany, the Nordic area, mainly Sweden and Denmark, UK and France. And we have also an office in Turkey, in Istanbul. Enginesoft is a multidisciplinary engineering company. Here you see a short list of our activities. We mainly focus on FEA and CFD, and the main topic today is computational fluid dynamics with a specific method that is the particle-based simulation method, but we also apply traditional mesh-based simulation methodologies. We also have software and people specialized in processes, simulation, and several other disciplines from crash to multi-body, acoustics simulation, electromagnetic, 1D fluid dynamics, and also treatment of large databases from experimental data. And last but not least, process integration and design optimization is the core of what we do. Process integration means that we can build simulation processes including several of these boxes, several of these disciplines, and apply design optimization, DOE methods, and statistical analysis to numerical data and to experimental data. This is just a quick overview of what we can do and of our expertise. Now we will enter more into the details of computational fluid dynamics and particle-based simulation. The name of the software that we use and that we will show is Particleworks. And the key benefits, the main features of this software with respect to traditional CFD methods is the fact that Particleworks is a mesh-free method based on particle simulation. So it means that the fluid is discretized by particles and not by a computational grid. This means that the pre-processing, the preparation of the model is easy and fast, even for very complex geometries, and even when you have to deal with the moving bodies, moving boundaries. One of the main features is the capability to solve easily and in an accurate way free surface flows, like you see in some of these pictures. And the third point is about the possibility to couple the CFD solution to rigid bodies, so calculation of motion of rigid bodies interacting with the fluid flow, and also the possibility to couple the fluid solution with the powder calculation, so granular flows interacting with fluid flows. These are the three main features, but during the presentation I will show more, and you will understand some of the main capabilities of the software. Just to give you a short and brief introduction about the method. To the left, you see the conventional method, typically finite volume method, that is the Eulerian approach that is used in most of the commercial CFD software. You start with discretizing your volume with a grid, with a fixed grid, and the variables of your problem, typically pressure, velocity, temperature, turbulence values, are calculated on the nodes or at the center of the cells of your computational grid. And the mesh is typically fixed. It can also be deformable. It can be moved and deformed, but managing these kind of applications with a deformable mesh or moving mesh is typically quite complex and requires a certain degree of experience. To the right, you see the MPS method, the moving particle simulation method, that it's a Lagrangian approach. It's based on a Lagrangian approach. It means that you discretize your fluid volume by particles. The particles are not fixed, but are moving, and you follow the particles as they move. It means that the variables pressure, velocity, and temperature are not calculated in fixed points of your computational domain, but they are calculated on the particles as the particles move. So you follow the particles trajectory and you calculate the flow field using the particles as the equivalent of the mesh elements. Just to show you how it works for a very simple case, and then we will show how it works on a more complex. To the left, you see the finite volume method, the conventional method. You have a simple box with a computational grid. You want to initialize the flow to simulate a water column, and what you do is to define the volume fraction of water and of air in two parts of the domain. The light blue volume is the one filled with water initially, and the white one is air, and you see the fixed mesh. To the left, you see the MPS method. What you have to do is simply import the geometry of the system. In this case, it's a simple box, and you have to locate the particles, the initial location of the particles. You don't have to build any mesh. You don't have to build any computational grid, and this is the starting point for the simulation. This is what we will see in the example that I will show in some minutes. And we will also run one simple simulation. So this is the idea behind and the main difference between the two methods. And let me show you how it works, this methodology, on real cases, on some applications that are the typical applications where traditional, conventional, mesh-based CFD struggles to simulate. And the MPS method is instead quite comfortable with and can easily simulate this kind of complex free surface flows with moving boundaries. So simulation of oil interaction with a crankshaft or with the pistons. This is quite easy to set up and to run with Particleworks by defining the volume, importing the CAD geometry, defining the initial oil level at the bottom in the oil sump, and then define the motion of the solid walls. The same methodology can be applied to study sprays, so free surface flows, but also sprays. This is a typical application for engine cooling, piston cooling applications. So where you want to define and calculate the the oil distribution on the piston walls, visualize the oil filming and the areas covered with oil or not covered with oil, and calculate the heat transfer coefficient on the walls of the piston, to calculate also heat transfer on the walls. So free surface flows, spray simulations. This is a transmission simulation. The example that I will show in the software is very similar to this one. So you will see how to set up the motion of the gears, how to set up the initial oil level, and how to start the simulation with the rotating gears. And you see the oil distribution. The typical output from these kind of simulations is oil visualization of oil distribution in the gearbox, calculation of churning losses, calculation of oil flow rates through the channels or in specific areas of the gearbox to understand the lubrication level, maybe changing the oil level or the rotational speed or the oil viscosity values. And you also see two different ways of visualizing the results. Here you see every single particle. This kind of visualization is instead a surface rendering, where you post-process the results to reconstruct the free surface from the particles. And as you can see, you can visualize flows, oil filming. The same can be applied for large systems like aquaplaning simulation or wading simulation, so interaction between vehicles and water. The definition of the motion of the car or the definition of the motion of this tire is quite simple, because you don't have to deal with moving mesh, deforming mesh, or overset mesh. You just apply the motion to the geometry, in this case to the tire, and you define the initial fluid volume, and then the output of the simulation is the interaction between the moving boundaries and the water in this case. Aquaplaning simulation, this is instead something a little bit more complex, because it involves not only the CFD simulation, but also the multi-body simulation, so the vehicle dynamics. You see the interaction between the moving vehicle and the water flow. You can visualize the internal flows. And you can also calculate by coupling CFD with a multi-body solver. You can also calculate the rigid body dynamics. You see that when the vehicle enters the river, you see the vehicle starts floating initially, and then it stabilizes. So this means that the fluid dynamic forces exerted by the fluid on the vehicle are accounted for in the definition of the motion of the vehicle itself. So this can be done by coupling the CFD software Particleworks with a multi-body software Ecodyne and performing a co-simulation. That means that at every time step, the two software transfer information to each other in order to calculate both fluid dynamics and rigid body dynamics at the same time. The same methodology can be applied to chain transmissions. Again, the motion of gears and chain is calculated by the by the rigid body solver, while the flow field, the oil flow field, is calculated by the CFD solver. So to the left, you see again the visualization of the particles, single particles. To the right, you see the surface rendering of the same solution, fluid solution. So you can see the oil lubricating the chain and interacting with the motion of the chain. And again, this is done by coupling multi-body and CFD simulation. The same methodology, CFD in this case only, can be applied to simulate other sort of free surface flows like sloshing in a fuel tank or any sort of free surface flow. Particleworks can also include non-newtonian fluids, high viscosity non-newtonian fluids. This is a mixer. So any simulation related to mixing of high viscosity flows, different kinds of flows of fluids, but also mixing between powder and liquids can be done. In this case, you see at the top, on the free surface, you see some solid particles. And what is calculated by this simulation is the mixing between the fluid at the bottom and the particles and the solid particles at the top. So the CFD software actually includes also a discrete element method that can be automatically coupled to the CFD solution. It means that you can solve for granular flows and fluid flows at the same time. Again, very complex geometries that it's almost impossible to simulate with a traditional mesh-based software can be easily handled in this mesh-based methodology. You see the mixing between two solid materials in a screw extrusion system. Mixing but also melting of solids can be simulated, so accounting for heat transfer and accounting for phase change is something that can be done inside Particleworks. So you see the mixing level between the two materials. And you can calculate also torque applied by the fluid or by the solid on the screws, forces, and pressure levels. Okay, we can start with more specific applications. So this was just an overview of some of the applications, and what I showed is something that is typically hard to simulate with the traditional CFD. I will show you two specific examples. One is related to a gear rotor pump, and I will show also the comparison between the NPS methodology and the mesh-based methodology. A comparison that was done on exactly the same geometry, exactly the same kind of simulation by using two different software methodologies, two different CFD methodologies. So we are talking about a gear rotor pump. The aim of this comparison was to compare ease of use and pre-processing time for the NPS method, for the mesh-based and particle-based methodologies, compare simulation time, and compare accuracy in terms of flow rate calculation. So this is a gear rotor pump. You have two rotors, the blue one and the red one, rotating at different rotational speed and with a certain eccentricity. And the system is a closed loop. And so the idea is that we want to calculate the flow rate, assuming there are no pressure losses in the system. Just to give you an idea of the results, this is what you get from the NPS simulation. The accuracy of the results was comparable in terms of flow rate calculation. So the main parameter, the main output parameter to understand accuracy was the flow rate. You see the main flow at the outlet, velocity distribution. This is top view and this is front view. And this is the comparison between the two methodologies. We compared in terms of setup time, geometry preparation, and physical setup, CPU time, hardware, and number of cores, and total time to obtain the results. The main benefit of the particle-based simulation is both during the setup. What you have to do is just to clean up the geometry, make the geometry watertight. You don't need to generate the mesh, so after cleaning the geometry, you can start directly with the physical setup. The physical setup take on average 10-15 minutes, depending on the complexity of the rotors. But it's very, very fast. So the main savings is due to the fact that you don't have to build the mesh. And this, for a complex geometry like this one, could take up to 2 weeks if you have to build a computational grid using overset mesh. The second benefit, the second level of benefit is in terms of CPU time. We compare the two methodologies for 2 rotations of the rotors. That means 0.12 seconds simulation. This took about 18 hours on 50 cores average, while it took 1.5 hours, let's say less than 2 hours, on 16 cores using the particle-based simulation. And the Particleworks software can also be faster, even faster. Using GPU calculation, it can be twice as fast as on 16 cores. This means that from the CAD to the solution, it takes less than 1 day using the NPS method, and it typically takes 2 weeks using the mesh-based CFD methodology. So the potential savings is about 9 days, even more than 9 days. Accuracy is the same, and if you look at the CPU time, at this kind of CPU time, it means that with this kind of methodology, you can afford to simulate very long periods of physical time, 1-2 seconds, in the same amount of hours that you simulate fractions of seconds. That means that in some cases, it can allow you to not only visualize the main quantities, but also to see the transient evolution of the flow in the system for a long period. The second application is a 2-speed reduction gearbox. The aim of this kind of simulation was to compare lubrication, changing the geometry of the system, changing the initial oil level, and also changing the rotational speed of the system, of the gears. The lubrication level was evaluated by calculating the flow rate, the oil flow rate in specific areas of the system, like the bearings, the channels that bring to the oil to the bearings, but also comparing churning losses. Here you see what is typically done for this kind of systems. The only way to understand lubrication is to do laboratory tests and visualize the oil flow field. It's very hard, almost impossible, to measure oil flow rate and understand what is really happening inside. So that's why we built this model, and by obviously building this model, you can visualize what happens inside and measure. So first of all, you see from the comparison between the experimental results and the numerical results, the behavior at the top of the gearbox. The transparent wall that you see here is the top wall of the gearbox, and you see the oil distribution on the wall. The main idea is that if you see oil on the top surface of this gearbox, then lubrication is good enough. If you don't see oil filming and oil flowing on the top wall, it means that lubrication is not good enough. First of all, we validated this by running the first simulation using a known geometry and known operating conditions, and we visualize the oil distribution at the top and the oil droplets falling down and lubricating the upper gears and the bearings. In order to compare the lubrication for different configurations or different oil levels, we also needed to calculate quantitative, so numbers. We need to calculate oil flow rate. So we selected some areas like the channel here that brings oil to the bearings. We located some monitor points there, and we measured the flow rate with the CFD model. And we were able to compare different solutions, different oil levels, and understand if different designs of the gears, of the hub balls, for example, could improve lubrication or could affect in any way lubrication. I will show you how to set up this kind of simulation in Particleworks to give you an idea of how it works and how simple or complex it is. Let me show you the interface of Particleworks. This is the graphical user interface where you have everything from the pre-processing to the solution to the post-processing. I just create a new project from scratch. I give a name to this project. And I open the pre-processing page. That is this blank page with a box that is the computational domain. Let me switch to orthogonal view. And you can select the wizard to set up the simulation. The idea is that you start with the definition of the objects of your simulation, that is mainly the CAD geometry, inlets and outlets, or fluid volumes. I select the CAD geometries, that is the gears. In this case, we have 5 separate CAD files that I can import. The reason why they are separated is that some of them will move with a different low, with a different motion, about a different axis and with different rotational speed. That's why I need to import them separately. What I do, first operation, is to, okay, this is what I imported. The computational domain is much bigger than the real geometry, so the first operation is to adjust the domain dimensions. I just tell that the domain dimension must be 1% larger than the real geometry, than the CAD geometry. So now the computational domain fits the CAD geometry. I can make the external housing transparent to visualize the other elements of the geometry, and I can start working on the gears. I select gear 1 and 2 that are the same geometry. Let me change the color to make it easier to understand what I will do. So I just give different colors to different gears. Okay. And I can start setting the physical properties and the rotations of the gears. So let me start with the gear 1 and 2, the yellow one. I locate the rotational axis automatically, centered on the body, and I can specify the rotation and the rotational axis quite easily about the z-axis, and I specify the rotational speed using a very simple way to specify time functions to define the rotational speed. This is quite simple because it's constant. I can preview the motion to be sure I set correctly the motion. And I can go on with the other gears. I select the green one. I locate again the center of rotation in the reference frame. I specify the direction of the rotational axis. And again, I use the same methodology to apply the rotational speed. I can do the same for the shaft. That is the gray body here. Rotational speed, axis, and RPM versus time. And then the red gear, center of rotation, direction of the axis, and time function. And we can check the motion. So it looks fine. So I have the objects, the elements, I have the cut geometry, I have the motion. I have now to specify the initial oil level. I can do in different ways. One of the easiest way is to fill initially the fluid volume by defining the oil level using a plane. I locate the plane, I give the direction, and I specify the position of the plane according to the volume or to the initial oil level in my system. So these are all the objects that I need to define my simulation. The next step is to create oil and wall properties, and this can be done by this physical property manager. I can add 4 types of materials. The first one is fluid. I can give again a name and specify properties like 8,850, and I can use some numbers that can be similar to oil properties. When I define oil, I just have to specify density, kinematic viscosity, surface tension coefficient, and heat properties, specific heat and thermal conductivity. If I want to solve also temperature, and then I can specify non-Newtonian laws if I want to use non-Newtonian fluids. The second type of material that I can specify is walls. Simple walls, boundary conditions that define the limits of my domain, the limits of my geometry actually, and it can be adiabatic or with heat transfer. And then I can also apply solid materials. That means that I can solve heat conduction and conjugate heat transfer, or I can add powder to solve granular flows together with the fluid flow. In this case, I only need oil and polygons, so to define walls, and I can also specify how walls and oil interact by specifying the contact angle between the liquid and the wall. This is the fluid definition and the solid definition and the material definition. What I have to do then is to associate material properties to the objects. In this case, I associate oil to the fill operation. It means that this volume below the plane, below the fill plane, will be filled with oil particles. All the rest is walls, stationary or moving walls. It doesn't matter the type of boundary, the type of material is the same. So this is the association between objects and physical properties, and the next step is to define particle size. When I define particle size, I just have to enter the one number, that is the particle dimension, that will be the resolution, the discretization of my fluid volume. So this is just one number. This is in meters, and it's 5 millimeters in this case to make it faster, this kind of simulation. But typically for this kind of application, the particle dimension is lower than 1 millimeter, depending on geometrical details and on how accurate you want to be. Next step is to define numerical. Okay, is to define first of all gravity. In this case, in minus y direction. And then you have to select numerical models to solve the pressure, to solve viscosity and the surface tension. You can also include turbulence. You can include heat transfer if it's relevant. Then you are ready to start. Last but not least is the initial time step and the total simulation time and the output frequency of your results. So this is used as the initial time step for your transient simulation, and this is the total simulation time, and your results will be saved with a certain frequency every 1 to the minus 2 seconds. It means that you will be able to visualize results with this kind of frequency. That's all, and you are ready to execute the simulation. There are 2 stages. The first one is the pre-processing. As you see, you can run the pre-processing, but also the simulation in parallel, depending on your course. And this is the start of the simulation. As you see, the simulation and the output files will be visualized in the same environment, just a different window. So you will be able to check your geometry and your model, set up your model, and run the simulation in the same kind of environment. The pre-processing phase takes some minutes because you have to define, the software has to define the walls, to characterize the walls of gears and housing and all the rest, and then the software will have to fill the initial volume, the volume below the plane, with particles of the given dimension, in this case 5 millimeters. So what we will see at the end of this pre-processing phase is the volume filled with particles, and this will be the initial state for the simulation. During the pre-processing phase, also you will be able to, at the end of the pre-processing phase, you will be able also to see the number of particles. The number of particles is the equivalent of the number of mesh elements in your model, if you refer to the traditional mesh-based simulation. And this will give you an idea of how large your model is, and will allow you also to estimate the simulation time as soon as you start the simulation. In this case, the number of particles will be quite small, about 12,000. When we ran the real model, okay, now the pre-processing has completed successfully. You see the number of generated particles, that is about 12,000. And if you go to the scene, to the project, you see the particles according to the fill level that we specified initially. Now we are ready to start the simulation again. And as I said, you see, this is the output file of the simulation. As it runs, you see the number of particles that in this case must be constant because we are simulating a closed system. You see the time step, and the time step is automatically adjusted by the software during the simulation. You see the physical time, 0.07 seconds, and the elapsed time and remaining time for your simulation. And here you see also the output state. This number means that we have 9 results files available, and if you go to the project view, you can visualize and play the movie of what is happening inside the system. So you can scroll time and visualize particles and how they behave inside the gearbox. You can stop and restart the simulation. So you can resume the last frame, number 19, and restart again. So that's quite easy to manage and quite fast to run in this case.